Welcome to this my presentation of this second virtual conference of ICSOBA. The subject of my presentation is a review of the SAMI retrofit project in QTX Smelter in China. The co-author Keng Sun is from SAMI. They are responsible for this project, retrofit project that was took place in China. I was involved indirectly by training SAMI on the modeling work that will be presented. So the introduction is coming, and then after that we'll present the modeling work. Essentially two models, magnetic model and thermoelectric model. And after presenting the initial operating result from the previous technology and then KPI of the new technology will be presented. So far in China, the expansion of the industry, major expansion, was done by greenfield project from initially 300 kilograms up to 600 kilograms in the last project. Especially for SAMI, the type of technology that was implemented. We can talk about SY 300, 350, 400, 500, and 600 kilograms. They were able to develop that kind of technology through their expertise in modeling. And they started, and now in China, it's very actively done currently. A lot of retrofit projects are being done because they are not allowed to construct new greenfield smelter, except if they're closing older one. So the only way to keep capacity is by retrofitting existing smelter, and that's what they're doing now. And they started to do that. Most probably one of the earliest, if not the earliest project, was this QTX project. So we're going to present this QTX retrofit project. So the initial technology was implemented in 2004 by GAMI. The name of the pot is GP350. And I'm going to present the KPI of that technology next. That technology have some deficiency typical to this kind of generation of a smelter in China. Excessive ledge on the cathode, especially in the corner, and instability after anode change. So this is the schedule of the implementation of that initial GP350 technology. So started the construction in 2004, finished about 2 years later. And operating up to 2008 with that design characterized by the KPI that is here. So 350, 90.5% current efficiency, low excess LF3, 5.5, relatively high temperature corresponding, and relatively high metal level to stabilize the cell. So this is the technology that was in operation up to the point where SAMI was asked to do a retrofit. So in 2008, they were asked to analyze the situation. So they developed the first magnetic model. The type of magnetic model SAMI is developing based on ANSYS, and they are typical of what I have presented first in a paper in 1994. So in ANSYS, when you lattice finite element to solve a magnetic field with a ferromagnetic component of the punch shell, you need to mesh the air, that is the green mesh here in this figure. So their model are similar. So they are not presenting the exact model they have developed for this project, but they have presented in the past similar model, like their model of the SY 300 kiloamps. on the left, and then the SY350 on the right. The 350 is SY350 is very similar to the GP350 from GANI. They have 6-riser both technology that we can see with the 6-riser. So what's missing on those two figures is the mesh of the air that was presented in the previous slide. And what is missing on this on the right is the pot shelf that is shown here on the left. But all models, all ANSYS magnetic model, they are the same. They require the meshing of the pot shell in 3D and the meshing of the air around the pot shell to solve the magnetic problem. And what you get out of the solution is the magnetic field inside the liquid zone, especially the middle of the metal pad, where we are especially interested in the vertical component, and we want to reduce as much as possible the gradient in that long direction of the pot. And right now it is going from 30 Gauss plus to 30 Gauss minus, and according to Urata, this kind of gradient, here we have the plus on the right, the plus magnetic field and negative vertical component, will introduce a rotating wave following this pattern of when you have this configuration of the metal pad, you have a force that is pushing in one direction and pushing the metal pad in that configuration, creating a force that is pushing out on both ends, hence the creation of this rotating wave. So this is well known, and then knowing that, well, the aim of the retrofit is to reduce this gradient. Next model is the thermoelectric. So they are also using ANSYS. They are using the type of technology I trained them to use in 2005. So it's here I'm showing the first model I've presented in a paper in 1991, where the ledge is converged as part of the solution. So in SAMI, they have, after the training, they are using a similar type of model, and they are presenting two of those in papers. The SY300 on the left, that is fully 3D, even if the next two slides or picture are showing only 2D result here in full color, and here only in lines. But that's the model is geometry is full 3D, like we can see here. No liquid zone, and with the logic to converge the ledge profile to the melting temperature of the ledge. So this is the technology that they are using, they have used for this study. Okay, now what have they done? First, one thing extra is their validation. They have validated their modeling technology. And here I'm going to show some validation work done for the SY400. So here you have for validation, you measure the heat balance around the pot, you measure the ledge, and then you ensure that your model is reproducing the measurement. This is the way you establish the transfer coefficient you use in the model to predict the ledge profile. That's part of the training when you learn how to do this model. Okay, so now we have the magnetic model, we have the thermoelectric model. Time to design with those models. So the first thing that they have done is introduce two compensation loops to reduce the gradient of the vertical component of the magnetic field. Typical compensation loop introduced first by Pichini. So this is the sketch of the compensation loop that were introduced. Inner loop of 60 kiloamps and an outer loop of 30 kiloamps running in the same direction of the pot line and both ends of the pots. So this kind of introduction of a compensation loop produced this result. It's flattening the component, vertical component of the magnetic field, as predicted here by the ANSYS model. So instead of having a plus minus 30 gout, now we have a plus 10 and minus 15 according to the scale here. And what they have done is that they have introduced these compensation loops, and then they measured the result. Here it's on the upstream side, average decrease from 30 to 10, 20. So maybe a reduction of a factor a bit more than 2. So not maybe as drastic as predicted by the model, but quite close. And this is the downstream side. More clear reduction on the duct end, not much on the tapping end. So this was studied in magnetic model and then implemented and measured. Second thing you can do to improve stability is to you change the lining design, and you introduce a way to reduce the horizontal current that are also bad for stability. So the JY, so the current density in the metal in the Y direction, that is the short direction of the path. And they have done that by introducing a technology that they name HCRT, but they don't describe what it is. I'm aware what it is because of another project that I'm involved in. So it's good to know that this type of technology has been implemented a long time ago and gave some good results. That's all I can say about it, except the result that is by introducing that technology in the lining, they can reduce the intensity of the horizontal component of the density in the metal pad. So those two changes are the two changes implemented in that QTX smelter. So now I'm going to present the schedule and the results. So it was in 2008 they started the study. They got the mandate and started the study. They have installed the compensation loop in 2010 and the lining design in 11 and 12. And they went from the capacity creep is by increasing the amperage from 350 to 370. At the same time, they gain a lot of energy efficiency from 14 to 13.2 kilowatt hour per kilogram. So what they have not done is any gain on current efficiency. They went from 90.5 that was presented initially, and now they are 90.7. So no gain on the current efficiency, but a significant gain on the power efficiency. So a drastic reduction of ACD for sure, while increasing the amperage. So that's the schedule of the implementation. So they got the mandate in 2008, implemented the bus bar compensation 2010. The pot was more stable right away, and then introducing the new line in end of 2011, and then creep the amperage to 370 with a more stable operation. New KPI, first step is only increase the introduction of the compensation loop. So they went from 90.5 to 93 from that first step. They increase the excess and decrease the temperature, so decrease the metal pad level. They don't quote the change of a ACD, but with the change of cell voltage, you and gain of energy gain of energy efficiency, you can assume they reduce the ACD quite a lot. And then that's the first step, and then the second step, they introduce the new lining and create the amperage to 370, and to get to 12 or 13.0. They claim in the previous slide 13.2 kilowatt hour per kilogram. Okay, so that's the more or less the full story of this retrofit. So the conclusion that the QTX smelter was retrofitted by SAMI successfully. So that's a demonstration of the expertise to do so. They are currently involved in many such retrofit projects in China, but they are also involved in a project that I'm more closely involved in Indonesia, in Arum. So this is that statement is from the announcement of the selection of SAMI as contractor, EPC for engineering, procurement, and construction of this. So the SAMI is coming. It's coming with the new design and then doing the engineering, the construction, the procurement, and the construction of the new technology for Inarum. And after the retrofit, the pot line that would be retrofitted will go from 194 kiloamps to 235 kiloamps. Thank you very much for your attention.